Welcome back to the third part of the APECE Econ Chemistry Chapter 6 homework review. Let's take a look at problem 25. In this particular problem, you're asked to find how many electrons in a given atom can have the following quantum number combinations. So if n equals 2 and L equals 1 and m sub L equals 0, there's a possibility for 2 electrons to have that combination of quantum numbers, one electron with a spin of plus a half and one electron with a spin of minus a half. If you are given a example like in part B, a particular electron pairing or a particular set of quantum numbers, when n equals 2, L equals 1, and m sub L equals negative 1, we're talking about one orbital, and again you can have two electrons that could exist in that, the plus 1/2 spin and the minus 1/2 spin. When you are dealing with, like in part C, something that has n equals 3, L equals 1, m sub L equals 0, and m sub S, the spin is plus 1/2, there's only one possible electron that can have that pairing of quantum numbers. Based on the Pauli exclusion principle, it's only possible for one electron in a specific atom to have 4 different unique quantum numbers as such. Let's take a look at 27. You're asked in 27 if these possible pairings of quantum numbers could actually occur. If yes, just say yes, and if not, kind of explain why. Why not? Why is it not possible? So if n is equal to 3, it is possible for L to equal 0. It is also possible for m sub L to equal 0, and it's possible for m sub S to equal negative 1/2. If n is equal to 2, it's not actually possible for L to equal 2. There's no D sublevel on the second energy level, n equals 2. Part C and part D are both yeses if you follow through the same sort of logic train. You'll notice in general that as you move from left to right that these values tend to get smaller in nature, and that's a good way to just kind of roughly check to see whether this possibility could happen. If we look at part E, this is definitely a no, because the last quantum number, m sub S, the spin quantum number, cannot have a value of 0. Let's take a look at question number 29, parts C and D. You're asked to write the ground state electron configuration for neon and nickel. So you need two pieces of help on this one, two tools. First is the periodic table, and then you also need access to the filling order, the Aufbau filling order. So learn how to reproduce this diagram. You kind of write out the energy levels and then the sublevels, and you move to the next line, write the energy level, and then all the sublevels present there. On a given energy level, n equals 1, there's only one sublevel, and then technically if we get down to n equals 6, there really are 6 sublevels. After 6F, there's 6G and 6H. We just typically, on atoms that are found on our planet, don't really find electrons in those high energy levels. After you've reproduced the diagram that's underneath there in the black print, you go on the diagonal and fill in that order. And that Aufbau filling order will put electrons in the lowest energy levels first. So with neon, there's no big deal. We find that neon on the periodic tables here has an atomic number of 10, therefore should have 10 electrons as a stable element. We got to find homes for 10 electrons. So we fill in S first, and the capacity of S is 2 electrons. Then we fill it on energy level 1. Then we proceed to the next arrow, energy level 2, 2s. Again, 2 electrons can fit within there. Then we proceed to 2p, which has the capacity of 6 electrons. And if we add up our superscripts, 2 plus 2 plus 6, we get 10 electrons, and by golly, we're done. For nickel, it's a little bit more involved, but we follow the same basic logic. Fill along these arrows, and we get our first sort of hiccup right here. After 3p, you may want 3d to fill, but before it does, a lower energy level 4s orbital fills with 2, and we get to D. The capacity for a D or a sublevel is actually 10 electrons, but we don't need all 10 spots because we only have 8 electrons to fill there. Just for your own sake, an F sublevel could actually fill 14 electrons.